All right, section 4.9, modeling with polynomial functions. Our objective is to write polynomial functions for sets of points. So we're going to be actually writing the equation today, writing that function, coming up with that f of x equals, and what does it equal, that equation. We're going to write polynomial functions using finite differences. Okay, and we're going to use technology to find models for these data sets. So you will need your calculator. So if you don't have it, please pause the video and go get it. All right, so now if you remember way back in chapter 1, and I'm actually going to pull chapter 1 out, okay, way back in chapter 1, we had a section on modeling with linear functions, okay? This is where we took data sets or equations, okay, or graphs, data sets or graphs, and we came up with the equation that will best model this data, basically that will best fit this data, okay? And in chapter 1, we did it for lines. We were graphing just straight lines way back when. You remember how nice our straight lines were, okay? So we were graphing just straight lines, okay? And then in chapter 2, we got into quadratic equations, squared equations, and we did this process again. We were modeling with quadratic functions. So here, again, we were given a graph or a set of data points. Okay, we used some of these finite differences. We took the differences, whether the first difference or the second difference. If it was the second difference, it was quadratic. If it was the first difference, it was linear. Okay, and we came up with those equations. Okay, we did it by hand using 3 different equations. I don't know if you remember that. Or we used our calculator and our stat plot to plot those points to come up with that equation. Okay. Now that we've gotten into higher degree equations, polynomial x to the third, x to the fourth, excuse me, sorry for bumping that camera, we're going to be doing this exact same process again. Okay, we're going to do some by hand, but we're also going to do some, again, using our calculator and that technology. Okay, all right, so first thing is we're going to do one by hand. Okay, we're going to write a cubic function. Again, remember that's x to the third. It's got an x to the third in it, whose graph is shown. So if it's cubic, x to the third, I know it's going to have 3 zeros. Some may be real, some may be imaginary, okay? But here we have this graph, and if we notice, all 3 of them, we have 3 x-intercepts here, which tells me that these 3 zeros are all real, okay? So since all of these are on my graph, they're all real, okay? So I have 3 real zeros, and my real zeros end up being here, this number, this -4, this 1, and this 3. So that tells me those are solutions of my equation. So I'll have an x equals -4, x equals 1, x equals 3. So now that I have those 3 solutions, those 3 zeros, we can write our factors. Remember from the last couple sections, we could write our factors. So my factor would be x plus 4, x minus 1, and x minus 3. The way that this one is slightly different than our previous one is that it needs to not only have those zeros, but it also needs to fit the rest of this graph, meaning it also needs to go through this other point they gave us here. It needs to go through this point right here, this blue point, the point 0, -6. Okay, come down and go through that point. So to make sure it goes through that point, there could be some constant multiplied out front, some a. Multiplied out front, that will either stretch or shrink or reflect this thing to make it go through that point. Okay, but we don't know what that a is. So that's going to be our first step, is finding that a. Okay, find what a is. So I know in this graph here I have the point 0, -6. What this tells me is when x is -6, or when I have an input of 0. When x is 0, or I have an input of 0, then y, my output, is -6. So when I input a 0 into this, so when I put a 0 in for my x, I get out a -6. So let's go ahead, let's put in a 0 for all my x's. 0 plus 4, 0 minus 1, 0 minus 3, but I get an output of -6. So now the only variable I don't know is a. So now I just need to simplify. It'd be a times 0 plus 4, that's 4, times 0 minus 1 is negative 1, times 0 minus 3 is negative 3, has to equal negative 6. So a times 4 times negative 1 times negative 3, well, 4 times negative 1 times negative 3, that gives me 12. A equals negative 6. Okay, and to find A, I'd have to divide both sides by 12. So my A is equal to negative 1/2. So then I know my function f of x, is going to equal my A, negative 1/2. And let's just leave it in factored form. X plus 4, x minus 1, x minus 3. And now I can double check this by graphing this in my calculator. So I'm going to go to my y equals. Oh, I think my lens might need cleaned up. It's looking a bit dirty. Okay. So we'd have negative 1/2 x plus 4, x minus 1, and then, parenthesis, having trouble, parenthesis x minus 3. If we graph this, it should look like that one, which it does. My window's a little different. I don't see all the way down to negative 16, but it will go through these points. Negative 4, I'm tracing. Negative 4, 0. The point 0, negative 6, 1, 0, and 3, 0. So we have the right equation. Okay. So there's how to write a cubic function if we're given all, for this one we had to be given all the real zeros. There are no imaginary, okay? If there's some imaginary, then that kind of, I can't find the exact equation. No imaginary, and we're given at least one other point, okay? Okay, if you remember back from chapter 1 or for chapter 2, okay, if we have equally spaced x values, equally spaced inputs. If you notice here, my input goes up by 1 each time. So it's equally spaced. Then we can determine what type of an equation we'll have by looking at the difference of the y value. So we would subtract here. So here I would take the 9 minus the 4. I get negative 5. I'm taking the 4 minus the 9. 1 minus 4 is negative 3. 0 minus 1 is negative 1. 1 minus 0 is 1. 4 minus 1 is 3. 9 minus 4 is 5. So since all of these aren't the same, these are my first differences. Okay, my first differences. Since all of those aren't the same, okay, then we would go on and do the next one. So negative 3 minus a negative 5 is 2. Negative 1 minus a negative 3 is 2. 1 minus a negative 1 is 2. 3 minus a 1 is 2. 5 minus 3 is 2. So there, if you see my second differences there are all the same. Since my second differences are the same, then I know this is going to be quadratic. It's going to be an x to the second. But this same rule applies if we keep going. If I keep going and if this wasn't the same, then we could go to the third differences, the fourth differences, so on and so forth. So I could have a fifth degree. If I go down and the fifth differences are the same, then it's going to be a fifth degree polynomial. This pattern continues for higher degree polynomials. Okay. So this can help us decide which one of our regressions we want to do in our calculator. So instead of having to do them all and look at those R values, we can use these finite differences to kind of eliminate some choices. Okay, so here, like in example 2, use finite differences to determine the degree of the polynomial function that fits the data. Then use technology to find that polynomial function. So we're going to go ahead and we're going to do some differences. I always like to kind of do those differences in my calculator. It removes any of that error. So it might seem silly, but we'll go 4 minus 1 is 3. 10 minus 4 is 6. 20 minus 10, well, that's 10. 35 minus 20, that's 15. 56 minus 35 is 21. 84 minus 56 is 28. Okay, so first ones didn't work. So let's go ahead, let's look at the second one. 6 minus 3 is 3. 10 minus 6 is 4. 15 minus 10 is 5. 21 minus 15, if you're not sure, we'll type it in, that's 6. 28 minus 21 is 7. So still not the same. So first, second, so it's not quadratic, so let's go again. 4 minus 3 is 1. 5 minus 4 is 1. 6 minus 5 is 1. 7 minus 6 is 1. So there we got them all the same. First, second, it's the third. So this tells me it's going to be degree of 3, which is cubic. Okay, so now that we know it's going to be degree 3, we can use our calculator to find it. So to do that, I need to go to my stat button. Stat right here. Hit my stat button. We want to edit our lists. So I'm going to come in. I don't know why that's so blurry, but I'm going to go up to list 1, list 2, clear out what's in there, arrow down. That'll clear what's out. Clear out list 1, arrow down. So now we're going to go ahead and put them in. 1, 2, 3, 4, 5, 6, 7. I'm just hitting enter after each one. Arrow over. 1 is 1. 2 is 4. 3 is 10. 4 is 20. 5 is 35. 56. 84. So I have them all in there. Okay. Now I'm going to go to my y equals. Y equals. I'm going to clear out what's in there, and I'm going to turn my plots on. Plot 1. So that's going to plot those points that are in my stat. Okay. And now I'm going to change my zoom. I'm going to arrow down and I'm going to do zoom stat. So basically it's going to zoom in around my statistics. It zooms in around my statistics. So there's all my points. If I wouldn't have done that, I wouldn't have been able to see them because they're way up at like 20, 35, 56. My y didn't go that far up. Okay. So now we know it's going to be cubic. So now I want to come up with that cubic equation. So we're going to go back to stat, over to calculate, and we want a cubic regression, which is option 6. A cubic regression. Okay, if your calculator doesn't look like this, you need to come in and see me so I can update your operating system. Okay, we do list 1, list 2. We don't do the frequency list. But I arrow down to store regression equation. I want my calculator to store or put this regression in my y equals. So I would go vars, arrow over to y vars, function, hit enter, and I want it to go to y1. Okay. Now I come down, go calculate, enter, and there it has, there's my equation, ax cubed plus bx squared plus cx plus d, where my a is 0.1666666 repeating. It looks like it's going to repeat forever. My b is 0.5. My c is 0.3 repeating. My d is 0. If you notice, it's a perfect fit. Your r is 1. That R2, if you remember from previous sections, is that correlation coefficient. It tells you how well your data, your equation fits the data, the table. This one fits it perfectly, which we could tell because I have a perfect finite difference here. Okay, so now let's write that equation. Okay, so my equation is my function f of x equals, I've got 0.1666 repeating. Okay, I'm thinking that might be a fraction. Okay, so let's go ahead and let's see what fraction that is. 0.166666666. I'm just going to do a bunch of them. And then we'll go math, enter, enter. It's actually 1/6. If we type in 1/6, we get that nice repeating decimal. So it's going to be 1/6 x to the third. Plus, I don't remember what the rest of it was, so let's go second enter until we bring it back. There's my regression. Okay, my b goes on the x squared, and that's 1/2 plus 1/2 x squared plus my c that goes on my x is 0.3 repeating, which again, I'm pretty sure that's a fraction. It's 1/3 x, and then there was no constant. My d was 0. Again, we can bring that back. My d was 0. To bring stuff back is just second enter. Okay. So there's my equation. And if you go and look at your y equals, it put that equation in your y equals. If you graph it, it fits these data points perfectly. It goes through every single point. Okay. All right, one more example. Okay, example 3. The table shows the total U.S. biomass energy consumption, Y, in trillions of British thermal units, or BTUSs, in the year T, where T equals 1 corresponds to 2001. Find a polynomial model for the data. Use the model to estimate the total U.S. biomass energy consumption in 2013. Okay, so it doesn't really tell you which one to use. So let's go ahead and let's try a couple. Let's plot the data and see what it looks like, and then maybe try a couple models and look at that R value. Okay, so let's go stat. We want to go edit again. I'm going to delete, clear. Don't hit delete, hit clear, arrow down. If you hit delete, the list disappears, and it's kind of a mess for me to fix it. I already have 1 through 7 in there, so I'm just going to do the rest, 8, 9, 10, 11, 12. This one doesn't tell you to use finite differences to find out which one works. And a lot of times in real life type data like this, you're not going to find a perfect finite difference just because it's real life data, and real life data is very variable. It doesn't always, very rarely fits a perfect. Okay, so I'm putting this in 3493. 3866, 3951. Okay, so now I got them all in. Again, I'm going to go to my y equals. I'm going to delete what's in there. My plot 1 is still on, but I'm going to go zoom stat again, so it zooms around my new statistics. Zoom stat. You can tell here it looks like we kind of have a bit of a curve like this, which may be cubic. Thinking maybe cubic, could be quartic or possibly to the 5th. So let's do cubic. Let's do a cubic model and a quartic to the 4th, and a quartic, and see which one fits it best. It doesn't look like a parabola at all, so I know it's not going to be x squared. Okay, so let's go to our stat button, over to calculate. Let's do a cubic. And let's store the cubic, again, list 1, list 2, go down, let's store that in y1, vars, over to y vars, function, y1, enter, and we can see my R value there is 0.98894. I'm just going to write down the R value for right now. Okay, so there's the cubic. Okay, and now let's do quartic, stat again. Calculate, quartic, option 7. Okay, but now I'm going to store this regression in y2, so I have them both there when I like them. Function, so I'm going to arrow down to y2. Calculate. Okay, my R value, I'm going to have to arrow down to find it. 0.994667. So which one was closer to 1? The quartic was closer to 1, so that's the one we'll go ahead and write down. So, and that's the one I have up there right now. So that function f of x is equal to my a negative 0.54. We'll go 2 decimal places. I'm going to need more room. Let's move this over. Oop, sorry, shaky. Negative 0.54 x to the 4th. Okay, my b is 11 point. I'm doing 2 decimal places, so go 11.49. 11.49 x to the 3rd. My squared is negative 68.77 x squared. Oh, still don't have room. Okay, plus my x is 264.97x plus 2395.19. Sorry, I had all this room and I squished it in right there. So there's my quartic equation, and then it says use the model to estimate the total U.S. biomass, which that's Y. The total U.S. biomass is the Y. Consumption in 2013. So there's my T. My T. So we want to know in the year 2013, which corresponds to T equals 13, because this is what 2001, 2002, so 2013 would be t equals 13. So now I'm just going to go to my graph, to my table actually, and remember we learned how to just type in a number. I'm going to type in 13. Again, y1 was my cubic, y2 was my quartic, so in my quartic it was 4,047.8. Okay, my cubic was 4384.8. Okay, and this is in BTUS's. I did both just in case. Sometimes you will notice some discrepancy in the book. The book will do one when the other one is actually a better fit. I just honestly think they do cubic most of the time when a quartic is actually a better fit in this case. So 4,047.8 BTUS's is what's expected in the year 2013. Okay, so let's write down your practice. Okay, and good luck. Come see me if you have questions.